Now, the examples that we have considered so far were all linear models, the single tank and the second tank. For example, for these tanks, we have assumed that the variation of the output is linear with the level in the tank. However, the actual case is not this. In the case of a tank, for example, we have the output Q out is related to the level in a nonlinear way, like this, k square root of h. So in that case, we cannot apply the Laplace transform analysis that we have demonstrated so far. And we need to do a process called linearization to convert this nonlinear system to a linear system that can be handled. Whenever you have a case where you have a nonlinear model, then you need to linearize this model in order to use the Laplace transform analysis and the transfer function representation for the process. To do the linearization, we need to use the Taylor series expansion. If you remember from your numerical methods course, the Taylor series expansion was used to mainly approximate functions. And it does this by representing the approximated function as a series of added terms. Now, if we have an ordinary differential equation of this form, and this f of x represents the right-hand side of the differential equation, the f of x, which will be some function, can be represented using or approximated using the Taylor series expansion, which has the general form of this and the expanded form of this. So what we can do is to take the first two terms of the Taylor series, only those first two terms. We don't need to go for higher terms. And then the approximation will be a linear function that is involving the differential term here. So actually f of x will be represented by the approximation, a line, which is a line, this line. This represents the tangent to the curve at this point. And we can do our analysis and represent this differential now, this differential can be represented as, of course, now this value is a constant. So actually it will be a constant plus another constant times the difference between x and x bar. Now, why x bar? Well, in a Taylor series, we can approximate functions if we know the value of the function at a certain value. So knowing the value of the function at a, I can approximate the value of the function at x. Similarly here, knowing the value at x bar, of course we know the value at x bar, that's the state value, I can approximate the value at x. And then using the deviation variables or perturbation variables, this will drop because its value now is 0, and of course this will be the perturbation variable, so x prime. And then our differential equation now can be represented as this constant times the perturbation variable x bar, which is linear. Now remember that we have started with f of x, which can be linear or nonlinear. So here we are considering the nonlinear case. And now we ended up with a right-hand side which is linear all the time. This is the idea of linearization. If we have a case of multivariable function, like here, dy by dt is equal to a function of u and y, then we need to use again the Taylor series expansion, but now about both the u and y. So we will linearize about the u bar and the y bar. And then our Taylor series expansion for the first two terms will be the value of the function at the steady state time the value of the differential at the steady state time the perturbation of u plus the value of the function derivative at steady state multiplied by the perturbation of y. And this means that if we have a nonlinear function like this, we can represent it like this. Now you can see that this is a constant, this is a constant, only u prime and y prime are variables. So now we have a linear representation for the function. So since at steady state we have the value of the function is equal to 0, and then substituting in the equation will end up of this definition for the derivative. We replace the derivative with the perturbation variable, and then the final linearized model will be this in perturbation form. Let's take an example and see how can we linearize a nonlinear model. The simplest nonlinear model that we can consider is the liquid storage system. Here, when we applied the overall mass balance, we ended up with this equation, and we know that the relation between Q and H is a constant, which we call it the valve constant, times the square root of H. We used to call it K, but here it's better to call it CV. A is the cross-sectional area of the tank. And now our model is dH by dt is equal to 1 over A times Qi minus CV square root of H. Now, we cannot do the analysis on this model directly. Why? Well, this is because we have a nonlinear term. Actually, this is a highly nonlinear term, and then the whole thing is a nonlinear model, ordinary differential equation. So we need to linearize this equation. We will solve this problem using two methods. In the first method, we will linearize the whole ordinary differential equation. As we proved in the previous slide, that the nonlinear differential equation can be put as a combination of two linear terms. Since we have two variables here, then this constant times Q prime, Qi prime, plus this constant times H prime. And this constant actually is the value of the derivative of the function, which is the right-hand side of the differential equation, at the steady state values of course, the derivative with respect to Qi at the steady state values. And here it's the derivative of the function with respect to H at the steady state values. So at the end we have a constant, we will call it A11 times Qi prime plus another constant times H prime, a linear differential equation. So we'll first find the A11, then we'll find the A12, and then we put them in an equation. For A11, we differentiate the function. Now the function is the function that we are talking about, this f, let me write it here. The function of Qi and H we are considering here is actually the right-hand side of the equation. This is the function. So when we say differentiate the function, we differentiate this expression. Differentiate it with respect to Qi, and substituting steady state values, we end up with 1 over A. Differentiating with respect to H and substituting steady state values, we end up with minus CV divided by 2A square root of H bar. This is a constant, and this is also a constant. So we can put them in the final form of the linear or linearized ODE. And if you look at this term here, we can define R, which is the reciprocal of this term. Now, if we just take the R remember there is an A here which can be separated, so CV, it will be 1 over CV over 2 square root of h bar. If I take 1 over this, will be called R. So R is 1 over CV over 2 square root of h. Then I can write the linearized differential equation this way. Here, h prime, which is this, over R, which is this. And that is why we've been using this expression when we analyze the tank system. So this h prime over R is the linear form of the CV square root of h. In the second method of linearization, we only linearize the nonlinear terms. So if you have a long differential equation and the nonlinear part is only small part of it, no need to linearize the whole differential equation. You just consider the nonlinear term. So if we go back to our example, we see that in this equation, the nonlinear term is this. This is only the nonlinear term, the square root of h. So it's better just to linearize it and convert the equation to a linear form. Now, to linearize it, we will use the same Taylor series expansion. So the value of the function at steady state plus the derivative of the function with respect to h at steady state times the perturbation variable. Okay, the differential will be 1 over 2 square root of h, and then combining these terms and defining the perturbation variables. So this will be replaced with h prime, and then this will be going to 0 because at steady state in perturbation variables the function will be 0, and then our equation will be square root of h prime is equal to 1 over 2 square root of h bar times h prime. This is a constant times h prime. We have linearized the nonlinear term. Then we can take the whole thing here and replace this square root of h, and then the equation will be linear. So we end up with this form of the ordinary differential equation, which is linear. Now, just to complete the analysis, we need to put it in a perturbation form. So we consider the steady state value, the steady state form of this differential equation. At steady state, this term will be dropped, and then also this term will go to 0. Then you will have only CV times square root of h bar. So this is the steady state form. Now, subtracting equation 7 from equation 6, you will end up with this form, knowing that the perturbation variables are defined and also the differential term is substituted with its perturbation form. R here is the same R that we have defined before, CV divided by square root of h bar. So you can see that we have reached the same form, the linear form, using the second method in which we have only linearized the nonlinear part of the differential equation. Of course, you are free to use any one of these two methods unless the question specifies the method. Okay, now let's take a few nonlinear examples and linearize them. We'll start with the Arrhenius form of the rate constant. You can see that this is a highly nonlinear function. Why? Because it contains the exponential form and also it contains the reciprocal of the temperature. So to differentiate this, we use the Taylor series, which says that this can be approximated by taking its steady state value plus the differential with respect to temperature at steady state value times the temperature in perturbation form. So this is exactly what I said. Now, the value of the function plus the differential of the function with respect to the t-bar times the perturbation variable for the temperature. And doing the differentiation, So we differentiate this function. This is the differential of the function with respect to temperature. And then combining terms and taking the k of t bar from both sides, we'll end up with this form. And you can know here that this form is linear because we don't have powers, we don't have reciprocals. Our variable here is just multiplied by constant. In the second example, this is a simple one. It looks very simple, just x times z, and multiplication is nonlinear. So in that case, we need to linearize. So the same thing, since we have two variables here, we have to use the multivariable form of the Taylor series, in which the y can be approximated by the combined effect of linearization of the two variables. So the y is its steady state value, which in this case will be x bar z bar, the derivative of y with respect to x at y bar, which is the z bar, times the perturbation in x. Then this is added to the differentiation of y with respect to z, which is x bar, times the perturbation in z. And this is the linear form of the equation y is equal to xz. So to summarize the method of linearizing nonlinear dynamic models, we have to follow these three steps. In the first step, step number 1, we perform first order Taylor series approximation for the nonlinear parts of the differential equation. Then we subtract the steady state form of the equation from the dynamic equation to then introduce the deviation or perturbation variables. Let's take an example for a CSTR with a first order reaction. So we have A, which goes to B, the rate constant is K, we have a constant volume reactor. So here we need to construct first a nonlinear model for this process, and then we need to linearize it in order to analyze it later on. Now, the nonlinear model for the CSTR can be constructed first by assuming, putting the assumptions. We have a constant volume, we have also a constant wall temperature, and we have constant properties. So here we will be doing a material component, material balance. This is the amount of component A that is consumed by the reaction, and this is the difference between the input and output amounts, rates of mass A in the reaction. Similarly, we can do the energy balance for the system. This is the amount of energy produced by the reaction, and this is the amount of energy transferred with the coolant or the heating system that we have. Here, so we have two differential equations, and then these are definitely, you can see that we have these red terms which are nonlinear. This is nonlinear, this is nonlinear. Now this part is linear because C node is a constant, so we have only Ca. Similarly here, T node is a constant, we have only T. The TW is a constant, and then we have a linear part. Only these two terms, this and this, are nonlinear, so we can just linearize them and substitute them in the equations. So considering this nonlinear term and linearizing around the T bar and Ca bar, which are the steady state values of the variables, we have two variables here, using the multivariable form of the Taylor series approximation, So the term is approximated by the steady state value of this term, which is a constant, plus the differential of this term with respect to t at steady state, which means that we need to differentiate this term, and then we substitute t bar and ca bar for the variables, times the perturbation in t, plus the differential of the term with respect to ca at steady state multiplied by the perturbation in ca. Doing this differentiation, first differentiation and the second differentiation, and substituting and replacing these constants. This will be a constant, of course, because it involves only steady state values. This is another constant, this is another constant. So our equation will be a naught plus a1 t prime plus a3 ca prime, which is a linear differential equation. Now we can take this linear representation of the term and substitute it in the two differential equations that we have developed. So replacing it for the first equation and replacing it for the second equation. Now these two differential equations are linear and can be solved using the Laplace transform. If we consider another example in which the reaction is a second order reaction with a time constant k, then doing the component mass balance on component A, you will get this equation in which we have now a more nonlinear form of the equation. K is already nonlinear, and we have also the squared. Now the Ca squared, if we assume that this is a constant, if K is a constant, then only the Ca squared is the nonlinear term, so we can linearize it using the previous approach and substitute it in the equation. However, if K is a function of temperature, then we cannot use this approach. Then we have to linearize both K times Ca squared, and then we have to use the multi-variable form in which we need the steady state value of these plus some constant, which is the derivative of the function, so we'll call this probably a1, times the k prime plus a2 times ca. And then now we have the linear form that we can substitute here. As a second assignment, you need to solve problems 3, 5, 10, 13, and 17 from Chapter 4 in your textbook. Submission will be 1 week after the announcement of the lecture and through Moodle.